Let's look at sequences and series. Suppose you want to add all the numbers from 1 to n. Can we find a formula for Sn? Okay, so here's my favourite way to see it. We have 1, and then 2, and then 3, all the way up to n. I'm going to just take n equals 3 to illustrate. And so for n equals 3, 1 plus 2 plus 3 is 6. But notice you could make the same shape so we've got this same triangular shape. And this is S3, and this is S3. And we can see from that rectangle that S3 plus S3 is just equal to 3 times 4. So S3 equals a half of 3 times 4, half of 12, 6. And you just extend that argument to n. Instead of an 3 by 3 triangle, we've got an n by n triangle. And then we put another n by n triangle here. And now this length is n plus 1, the height is n. So Sn, 2 lots of them, is equal to n by n plus 1. Therefore, Sn is half n plus 1. Done. Here's a challenge for you. If you're given a sequence of numbers, and this sequence goes 7, 11, 15, what's coming next? Obviously we're just adding 4 each time, so 19, ... Sum the first 10 terms. Pause the video if you want to have a go. Okay, it helps if we write this as 7 plus 4, 7 plus 2 times 4, etc. So that's really 7 plus 0 times 4 and 7 plus 1 times 4. So the first 10 terms, each term has a 7, so 10 times 7. That takes care of the 7s, and then we've got to add all these. 0 times 4 plus 1 times 4 plus all the way up to 9 times 4. So that is 70 plus 4 lots of 0 plus 1 plus all the way up to 9. But what is 1 plus da 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 plus 9? It's just a half times 9 times 9 plus 1. So we've got 70 plus 4 times that. Okay, so 4 times a half is 2. 9 times 10 is 90. 2 lots of 90 is 180. 70 plus 180 is, well, take 20 from the 70 and give it to the 180. 50 plus 200, 250. Now, formula booklets for maths in schools in the UK have a formula for summing a sequence that starts with a and then a plus x and then a plus 2x da da da, summing the first n terms. And to me this is really defeating the point of the maths curriculum, giving people these results to remember. It's useless. It's not a life skill. You're never going to need that in a life situation where you can't just go to Google and find it or figure it out. It should be about figuring stuff out. So let's figure out the formula. So n terms, we've got n lots of a plus, and then we've got x times 0, x times 1, x times 2, all the way up to n minus 1, because 0 to n minus 1 is n terms. So x 0 plus 1 plus all the way up to n minus 1, which is equal to a half n minus 1, n minus 1 plus 1, which is n. So n a plus x. So we could tidy this up a bit. I suppose there's an n here and here, so we could take that out. A plus x over 2 times n minus 1. You could probably write it, you could write it different ways, but I'm going to stick with that. That's as clean as anything. So yeah, another pointless formula that shouldn't be in that formula book. Now this sequence is known as an arithmetic sequence. Each time we add a constant amount, in this case 4. So this is an arithmetic I'm going to write a big M because it's arithmetic rather than arithmetic. Arithmetic sequence. And we also have a geometric sequence where to get to the next term you multiply by a fixed number. So a geometric sequence might look something like 3 times 2, that times 2, that times 2. You see, each time we're multiplying by 2. And this would be a geometric sequence. And a series is what you get from summing a sequence. So this 250 here, this is the 10th term of the arithmetic series. Yeah, the first term would be 7, the second term would be 7 plus 11, the third term would be 7 plus 11 plus 15. So you start with the sequence 1, 2, and you get the series. The nth element of the series is the sum of the first n elements, and there it is. So how do we find a geometric series? How do we sum up the first n elements of something like this? Well, the first thing to notice is whatever you start on, you can just move that outside. This is just 3 times 1 plus 2 plus 2 squared plus So the trick is, can we find a formula for, a closed formula for such a series? Do you see this isn't closed form because we've got that ... there. A closed form doesn't have that hand-wavy ... Okay, so let's, instead of using 2, let's use a general x. So we've got 1 plus x squared plus plus x to the n. And that is our Sn. There's a trick. What happens if we multiply this by x? So x Sn equals what? Well, can you see it's just going to shift everything to the right by one term. If you multiply 1 by x, you get x. If you multiply x squared by x, you're going to get x cubed. So that 1 is going to go to an x is going to go to an x squared, the x to the n minus 1 went to the xn, and we've got xn goes to a new term, x to the n plus 1. So the obvious thing to do would be to subtract these things, and this box will disappear. Giving you 1 minus x to the n plus 1. So Sn minus x Sn, that minus that is that minus that. What to do next? Well, let's factor out Sn. So, therefore, Sn equals 1 minus x to the n plus 1 over 1 minus x. Done. What is 1 plus a half plus a quarter plus an eighth plus ... Well, you could think of a square that's got area 1, and now we've got another square, but we're only taking half of it, and then we're adding a quarter, and then we're adding an eighth, and then we're adding a 16th, and then so on and so on. Can you see that as we keep on adding these smaller and smaller amounts, we're gradually filling up this square? And so the limit is 2. Let's introduce sigma notation. One plus 2 plus ... plus n as the sum as I goes from 1 to n of I. So how would we write this using sigma notation? Well, this is a half squared, this is a half cubed. 1 you can think of as a half to the power of 0. So it's actually a sum from 0 to infinity of a half to the power of I. Notice I didn't write the I here. I could have done, but you don't need to because it's obvious. There's only one variable in here. It's clear we're looping through. Okay, here's another one. The sum from 1 to n of I squared. What's that going to look like? Well, it's going to be 1 squared plus 2 squared plus plus n squared. And there is a formula for this, but it's quite tricky to find. The formula is n over 6, n plus 1 to n plus 1. Well, the first thing you'd want to try would be some kind of construction maybe that's similar to what we used for just summing the integers. You could think this is just 1 to the 1 plus 2 to the 1 plus plus n to the 1, so maybe there is some extension. But it's not particularly easy to find. Have a go if you feel like it. The method of proof I'm going to use is induction. And induction says if it's true for 1, and true for k implies true for k plus 1, then it's true for all k. And k has to be a positive integer, which is a natural number. So natural numbers 0, 1, 2, da da da. Those are the natural numbers. Now you can think of this like dominoes. Here's our domino 0. Here's our domino 1. Here's our domino k. Here's our domino k plus 1. So, if the first domino falls over, and every time the kth domino falls over, it pushes the next one over, and this works for all k, then all the dominoes are going to fall over. Yeah, you just push number 0 and they all fall over. Yeah, the important thing is to show this always holds. So let's have a go. True for the case of 1. Well, 1 plus nothing, because I equals 1 to 1. The sum is just 1, so the k equals 1 case, we've got 1, and the formula gives us 1 over 6 times 1 plus 1 times 2 lots of 1 plus 1, which is equal to a sixth times 2 times 3. 2 times 3 is 6. 6 over 6 is 1. And so we have 1 equals 1. And correct, it verifies. True. This is true for k equals 1. Now, let's suppose it's true for k. So we're supposing 1 squared plus up to k squared is equal to k over 6 k plus 1 2k plus 1. So, is it going to be true for k plus 1? So we are required to prove that 1 squared plus da 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 plus k plus 1 squared is equal to k plus 1 over 6 times k plus 2 times 2 lots of k plus 1 plus 1, which is going to be, well, what is 2 lots of k plus 1? It's just 2k plus 2. So 2k plus 2 plus 1, 2k plus 3. Okay, that's all we've got to prove. So 1 squared plus da 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 plus k squared plus k plus 1 squared. We already know this is equal to k over 6 times k times 2 k plus 1 times 2 k plus 1. Because we're supposing it's true for k. So this we can write as that. And we've got another k plus 1 squared. And that's the same. So what can we do here? Well, I can see there's a factor of k plus 1 in both terms, so let's take that out. And there's a factor of k plus 1 we want in our answer. And if we take out k plus 1 over 6, then here we've got k times 2k plus 1. And here we've got k plus 1, but 6 of them now. Does that make sense? If you multiply this term by this term, you get k plus 1 over 6 times 6 k plus 1 squared. There. So let's fiddle with this. 2k squared plus k plus 6k plus 1, so 2k squared plus 7k plus 1. So is that going to be the same as this? Well, let's multiply this out here. We've got k plus 2 and 2k plus 3. K squared, 4k, 3k is going to work, isn't it? 6. I made a mistake, didn't I? This was 6k plus 6, because I needed to distribute that over both terms. And we do have 2k squared plus 7k plus 6. So our proof, you can do this when you prove. You write the thing you are required to prove, RTP, up there. You can work backwards there, you can work forwards from your proof, and at some point you can connect them. And now if you read forwards there and back up here, we've shown that if it's true for k, so this holds, then adding the k plus 1 squared term we can manipulate and it comes out as that. So true k implies true k plus 1 and true for 1. Therefore, true all k in the natural numbers by the principle of mathematical induction. Now, in this case, it's not a particularly satisfying proof because we plucked this formula out of thin air. So, how would we figure out what to try and prove? It turns out this is generally a difficult problem if you're dealing with, say, cubes or to the power of 17. There's always a formula, but it's far from simple. So let's recap. What's a sequence and what's a series? Well, a sequence is just that, a sequence of numbers. An arithmetic sequence, you add a fixed amount each time to get to the next term in the sequence. A geometric sequence, you multiply by a fixed number to get to the next term in the sequence. So what is a series? A series is the sum of the first n terms of a sequence. So the third term of a series for a particular sequence is going to be term 1 plus term 2 plus term 3. And finally we've demonstrated proof by mathematical induction. For this particular example, summing squares. Finally, it's worth noting that here if x is between -1 and +1, but not including those endpoints, so if x is in the open interval, -1 to +1, then what can we say about S infinity? So imagine x equals 0.9. So you're looking at 1 minus 0.9 to a billion, 1 minus 0.9 to a trillion. This thing is just going to decay to 0. So S infinity is just 1 over 1 minus x. i.e., you can write 1 over 1 minus x as 1 plus x squared plus ... And this turns out to be a very useful result in many areas of maths. Let's test it quickly with x equal to a half, 1 plus a half plus a quarter plus that equals 2. 1 over 1 minus a half, 1 minus a half is just a half, 1 over a half is 2. So, correct, it worked. You get 2. Also, it's slightly bad form to write S infinity. You should really write the limit as n tends to infinity of Sn. And that's S infinity. But it's okay. Mathematicians know what you're talking about. Okay, done.